Would you survive on Earth's older cousin? If you woke up tomorrow on Kepler-452b, Earth's so-called older cousin, what would it actually feel like to take your first breath? Would the air burn your lungs or feel strangely thick and heavy? How much weight would you suddenly feel in your own body? And would the world around you be thriving or quietly, slowly dying? We like to imagine other worlds as exotic destinations, but Kepler-452b is different. This planet has been described as a kind of time machine, not just a distant point of light, but a possible preview of what Earth itself could look like a billion years from now. As our own sun brightens, as our climate edges toward a potential runaway greenhouse, this distant world might already be living through the chapter we have not yet reached. In the hunt for alien life, we usually ask whether a planet is in the Goldilocks zone, whether its orbit allows liquid water and a stable atmosphere. Here, the question is sharper. Can a truly Earth-like world stay habitable once its star starts to turn up the heat? Or is every planet like ours living on borrowed time, with a built-in expiration date for complex life and civilizations? Kepler-452b orbits a star remarkably similar to our Sun, but older and slightly brighter. This means it likely receives more energy than Earth does today. It should be noted that even a modest increase in stellar brightness, stretched over hundreds of millions of years, can push oceans, clouds, and climates toward dangerous tipping points. So if we stood on its surface, would we be looking at a lush blue marble or a world just beginning to overheat? Imagine the sensory details. The sky might still be a familiar blue, but with cloud patterns swollen by extra evaporation. Oceans, if they exist, could be more restless under higher gravity, with waves that hit harder and tides that feel heavier. Every step you take might feel like walking with an invisible backpack, as stronger gravity pulls at your muscles and bones. Even a simple act like climbing stairs, building a city, or breathing warm, moisture-rich air could feel subtly, relentlessly more difficult.
So, let's begin with a simple question that hides a profound risk. If Kepler-452b is already sliding toward a greenhouse future, what does that say about our own long-term prospects under a brightening sun? So it's time to find out the truth. By the end of this video, we will build a vivid, scientifically grounded picture of daily life on Earth's older cousin, from the color of the sky to the strain in your legs. And in that imagined day on Kepler-452b, we may glimpse the far future of our own world. Why this one planet could rewrite our future. But why does this one distant planet matter so much to us? When we talk about the fate of Earth, we usually look inward, to climate models and ice cores. Yet there is another way. We can look outward, to older versions of our own story, playing out around other stars. In the hunt for alien life, astronomers have now cataloged thousands of exoplanets. But while that sounds impressive, almost all of them fail as true mirrors of our world. Many hug their stars so tightly that their surfaces are baked far beyond Venus. Others drift so far out that any oceans would be locked under global ice. And a huge fraction orbit red dwarf stars with intense magnetic activity and flares that strip atmospheres. These are fascinating, but they are poor analogs for Earth's long-term future. Kepler-452b is different. It orbits a G-type star so similar to our Sun that astronomers nicknamed it Earth's older cousin. Its year is about 385 days, its orbit sitting squarely in the Goldilocks zone. The planet itself is about 60% larger than Earth, placing it in the super-Earth category, where it could still be rocky with a dense atmosphere and deep oceans. This means, for once, we are not comparing ourselves to an extreme outlier. We are looking at a world that might be what Earth becomes. It should be noted that the real key is the star. Kepler-452 is estimated to be roughly 1.5 to 2 billion years older than our Sun, and about 10% more luminous. Optimistically speaking, that age difference turns the entire system into a kind of time machine. By studying it, we can ask, how long can an Earth-like planet stay truly habitable before its star's slow brightening drives it toward a runaway greenhouse, stripping away oceans and sterilizing continents? So let's begin to see why this is so hard. We do not have a picture of Kepler-452b. We have only transit data, a tiny dip in starlight, repeating every 385 days, plus models of how sun-like stars evolve. Reconstructing life on Kepler-452b is like a cosmic detective case, where the crime scene is 1,400 light-years away, and the only evidence is a faint shadow and a stellar spectrum. So it's time to find out the truth. Under that extra 10% of starlight, is Kepler-452b still a blue world with thick clouds and temperate seas? Or has it already crossed the threshold into a Venus-like fate, with swelling oceans, choking skies, and the first whispers of planetary doom? In the next section, we will push those clues as far as physics allows. Meet Kepler-452b, the so-called older, bigger Earth. To answer that, we have to actually meet this world. What is Kepler-452b beyond a dramatic light curve and a few lines in a catalog? So let's begin with the discovery itself. In 2015, NASA announced that the Kepler Space Telescope had spotted a tiny, repeating dip in the brightness of a distant G2-type star in the constellation Cygnus. Every 385 days, almost the length of our own year, a planet passed in front of that star. From that simple rhythm, astronomers inferred a world about 1,400 light-years away, Kepler-452b. Why did that single detection send such a shockwave through the exoplanet community? In the hunt for alien life, we prize worlds that look, at least on paper, suspiciously familiar. Kepler-452, the host star, is effectively a solar twin, a yellow G-type star with a similar temperature and mass. The planet's orbit places it in the Goldilocks zone, where a planet could, in principle, sustain liquid water on its surface. This means Kepler-452b receives only about 10% more stellar energy than Earth does from the Sun. It should be noted that this is why the headlines called it Earth's older, bigger cousin. The star appears 1.5 to 2 billion years older than our Sun, shining roughly 10% brighter. Imagine looking at an alternate version of our own system, but advanced along the clock of stellar evolution. If Earth is a middle-aged world, Kepler-452b might be what a slightly future Earth looks like under a slowly intensifying star. But while the orbit and starlight feel comfortingly Earth-like, the planet itself does not quite match our scale. From the transit depth, Kepler-452b's radius comes out to about 1.6 times that of Earth. That puts it firmly in the super-Earth category, a regime where the rules start to change. Is it a scaled-up rocky planet with deep oceans and continents? Or has it crossed the line into a mini Neptune, wrapped in a thick envelope of hydrogen, helium, and other volatiles? With only the radius, we do not yet know its exact mass. But if we plug in plausible compositions, surface gravity could easily reach 1.5 to 2 times Earth's. Try to picture that. Every step would feel leaden. Mountains might slump lower. The atmosphere could be thicker, clinging more tightly to the planet, reshaping how winds blow, how clouds form, and how water cycles between ocean and sky. Optimistically speaking, that extra gravity might help Kepler-452b hold on to a dense, protective atmosphere and stable seas. Less optimistically, it might also trap more heat, turning that extra 10% of starlight into a slow, relentless pressure cooker. So is this truly an Earth-like haven, or a heavy, humid world already drifting toward a runaway greenhouse? In the next section, we will push past the basic catalog numbers and explore what its climate, oceans, and skies might actually be like. How we read a world we can't see. We've been talking about what Kepler-452b might feel like, But how do we know anything at all about a planet we can't see, can't visit, and can barely detect as a faint wobble in starlight? To answer that, we have to rewind to the telescope that found it. The Kepler Space Telescope did something deceptively simple. It stared at over 150,000 stars continuously for years and measured their brightness with absurd precision. Whenever a planet crossed in front of its star, Kepler saw a tiny, periodic dip in light. From that single repeating shadow, it could extract the planet's size and its orbital period. This means that for Kepler-452b, we know how often it orbits and how big a bite it takes out of its star's light. Combine the transit depth with the size of the star and you get the planet's radius, about 1.6 times that of Earth. Combine the orbital period, roughly 385 days, with the star's mass, and you get the distance of its orbit. From that distance and the star's brightness, we can calculate how much energy the planet receives. So let's begin to layer in more information. Kepler-452's spectrum tells us it's a sun-like star, but older and slightly brighter. Stellar evolution models, which track how stars age and brighten over billions of years, suggest it is around 1.5 to 2 billion years older than the Sun and about 10% more luminous. It should be noted that this extra luminosity is crucial. At essentially an Earth-like orbital distance, that 10% boost in starlight becomes a long, slow planetary heat lamp. Here is the pattern interrupt. We have no image of Kepler-452b, no continents, no clouds, nothing. And yet we can still play out its climate history. In the hunt for alien life, exoplanet climate models are our courtroom reconstructions. They take the hard numbers we do have, planetary radius, estimated gravity, insolation, star type, and run them through physics. How atmospheres circulate, how oceans store heat, how clouds reflect or trap radiation, how greenhouse gases build up or break down over time. By tweaking assumptions about its atmosphere and oceans, we can simulate a cool, blue world with thick clouds, or a hazy, humid planet edging toward a runaway greenhouse. Optimistically speaking, these models let us narrow the possibilities. So it's time to find out the truth. With Kepler, stellar evolution, and climate simulations working together, we can't yet say exactly what stands on Kepler-452b's surface, but we can rule out whole categories of worlds and spotlight the most likely climates and the types of life that might cling on as its aging star slowly turns up the heat. In the next section, we'll step inside those simulations and ask, under which scenarios does Kepler-452b stay habitable, and under which does it cross the point of no return? Two futures, gentle green world or slow motion oven. So now we arrive at the real fork in the road. Is Kepler-452b still a gentle, cloud-wrapped super-Earth with deep oceans? Or is it already drifting into a slow-motion oven where those oceans are starting to boil away? Those are not just poetic labels. They are two very different physical outcomes for the same planet orbiting the same star in almost the same Goldilocks zone as Earth. In the hunt for alien life, this is where things become sharply binary. Either Kepler-452b has managed to keep a thick, reflective cloud layer and a stable climate, or its extra heat input has pushed it over a threshold that no amount of clouds can fully mask. In the first future, imagine standing on a rugged coastline under a slightly brighter sun. The sky might be hazier, the clouds taller and more tropical, but seas still roll against rocky continents. Gravity pulls at you with perhaps 1.5 to 2 times Earth's strength, pressing the atmosphere into a dense, protective blanket. This means sound would feel heavier, storms slower but more massive, and any life that evolved there would be built low and strong, hugging the ground against that constant downward tug. If that world still holds on to its oceans, complex ecosystems could be thriving. Forests of dark, heat-tolerant vegetation might drink in the extra starlight. Coastal shallows could host reefs adapted to slightly warmer water.
Optimistically speaking, an older, more mature biosphere might have had an extra billion years to diversify compared to Earth, all under a star that is familiar enough to be called our Sun's older cousin. But while that vision is comforting, there is a harsher alternative. Kepler-452b receives about 10% more energy from its star than Earth does, and its star is already 1.5 to 2 billion years further along in its life. It should be noted that as Sun-like stars age, they brighten. A planet in a once perfect orbit can be slowly forced into a runaway greenhouse, where warming causes more water vapor, which traps more heat, which drives even more evaporation. On a massive world that holds on to its atmosphere very efficiently, this feedback can be especially unforgiving. Oceans retreat, clouds thin or shift to higher, less reflective layers, and the surface bakes under a thick, choking envelope of steam and CO2. Any remaining life is not just adapting, it is racing an irreversible climatic clock. So which future is Kepler-452b living through right now? Is it a wet, thriving super-Earth, or a drying, dying preview of our own distant fate? So it's time to find out the truth. In the next sections, we will walk step by step through both scenarios and ask a harder question. When we feed the physics with real data, which side does the universe quietly choose? Who's talking to you and where we're going? So who is actually taking you on this trip? I'm Host, and this is Channel, where we follow a simple rule. If a planet might change how we think about Earth's future, we go there. In the hunt for alien life, we have visited red dwarf systems, steam worlds, and frozen deserts. Today, we are stepping into something more personal, an older, slightly brighter mirror of our own home. It should be noted that this episode is part of a broader journey. Across the series, we are tracing how stars age, how their habitable zones drift, and how that slow motion reshapes the chances for life. Kepler-452b is not an isolated curiosity in the sky. It is one point on a timeline that runs from Earth's past to Earth's distant fate. So let's begin by laying out exactly where we are going in this video. First, we will move outward and look directly at Kepler-452 itself, a sun-like star, but older, slightly more luminous, and already shifting its Goldilocks zone. How does a star like this evolve, and how long does it leave a planet truly Earth-like and habitable? Then we dive down to the planet. We will dissect Kepler-452b's orbit, its 385-day year, its 60% larger radius, and what that means for surface gravity and atmosphere. Is this a heavy, cloud-wrapped world where every step feels like walking through water, or a rocky super-Earth with familiar continents and deep oceans? After that, we slow the pace. We will run climate and ocean scenarios, from cool blue global seas to a world tipping into runaway greenhouse. This means asking how 10% more starlight over billions of years transforms coastlines, weather patterns, and the very chemistry of the air. Only then do we let ourselves move in. We will imagine everyday life under this brightening star, the color of the sky at noon, the weight of your own body, how a civilization might build cities, telescopes, and myths while watching its world very gradually heat up. Optimistically speaking, could such a species learn from its star early enough to survive? The high-level goal here is not just to ask, could it have life? That question is important, but incomplete. We want to know, what would it actually feel like to live there day after day? And what does that emotional, physical experience teach us about our own timeline on Earth? Pattern interrupt for a second. Imagine you already live on Kepler-452b. This episode is your house tour. Each segment is another room in this alien world. And for the next hour or so, we will walk through them together, from star to surface
to speculative civilizations and leave only when we truly feel what is at stake. So it's time to find out the truth about our so-called older cousin. First principles. What makes a planet livable anyway? So if this is our house tour of Kepler-452b, what actually makes a room in the cosmic mansion livable? Before we step through any doors, we need the blueprint. In the hunt for alien life, habitable is not a vibe, it's physics. We often hear about the habitable or Goldilocks zone, as if it's a magical ring where life just appears. But while that image is catchy, reality is more subtle. The classic definition is simple. It's the range of distances from a star where a planet could have liquid water on its surface. Not ice, not steam, liquid. This means enough stellar energy to keep water from freezing, but not so much that it all boils away.
So let's begin with the star. The star sets the energy budget. How bright it is, what color of light it emits, and how that light changes over time. A cool red dwarf drips out energy slowly and for trillions of years. A sun-like star, like Kepler-452, shines brighter and whiter, and it slowly turns up the dimmer switch over billions of years. The same planet at the same orbit can go from comfortably mild to dangerously hot just because its star has aged. It should be noted that the star is only half the story. The planet decides what to do with that incoming light. Size, composition, clouds, oceans, and atmosphere all determine how much energy is reflected back to space, how much is absorbed by the surface, and how much is trapped by greenhouse gases. Two planets at the same distance from the same star can live utterly different lives. Think of greenhouse warming as a thermostat with a fragile sweet spot. Too little greenhouse gas, and the world bleeds heat into space. You get a snowball planet, ice creeping from the poles toward the equator, oceans locked away. Too much greenhouse gas, and you cross a threshold into a runaway greenhouse, like Venus, where the surface becomes an oven and water is driven off into space. So it's time to find out the truth. Habitability is a balance beam, not a fixed label. There's another twist. Sun-like stars brighten over time. As luminosity creeps up, the habitable zone moves outward. A world that started in the middle of the Goldilocks zone can slowly be pushed toward the inner edge, then beyond it into permanent overheating. Optimistically speaking, you get billions of years of calm oceans before the crisis hits. But the crisis does come. Kepler-452b sits right at that turning point. It orbits a slightly older, slightly brighter, sun-like star, and it receives a bit more energy than Earth does today. A bit larger than Earth, it may hold a denser atmosphere and stronger greenhouse effect. This means Kepler-452b is not just an Earth-like planet. It is a test case for everything we have just laid out. A world where the math says things should be getting interesting or dangerous. And in the next part of our tour, we'll move from first principles to this specific system and ask, has Kepler-452b already stepped off the balance beam? Kepler-452, an older, brighter twin of our Sun. So if Kepler-452b is the acrobat, what kind of spotlight is it performing under? Because to understand this planet's fate, we first have to understand its star. Kepler-452 is, on paper, almost boringly familiar. It's a G2 type main sequence star, the same overall class as our Sun, with very similar mass and temperature. In the hunt for alien life, that kind of match instantly raises our hopes. A Sun-like star, an Earth-like orbit, a potentially habitable world. But while our Sun is about 4.6 billion years old, Kepler-452 is estimated to be 1.5 to 2 billion years older. That age gap changes everything. Stars like our Sun do not stay constant. As they fuse hydrogen in their cores, they slowly brighten. It should be noted that standard stellar evolution models suggest roughly a 10% or more increase in luminosity over billions of years. This means that a planet sitting in the same Goldilocks zone gradually receives more and more energy, even if its orbit never shifts by a kilometer. The habitable window does not slam shut. It glides past, almost imperceptibly. For Kepler-452b, that extra luminosity is the quiet threat. A brighter star pushes the climate toward the warm end of the spectrum. Ice lines on land and sea would retreat uphill and poleward. Evaporation would intensify, feeding more water vapor into the atmosphere. And water vapor is itself a powerful greenhouse gas. Step by step, decade by decade, the planet could be nudged toward a runaway greenhouse where oceans boil away faster than they can be replenished. Does that sound familiar? Here is the twist. Unlike a volatile red dwarf, which can blast its planets with violent flares and strip away atmospheres in dramatic bursts, a sun-like star such as Kepler-452 is relatively calm. Flares happen, but not in the same relentless, life-threatening way. So it's time to find out the truth. For worlds like Kepler-452b, the main long-term danger is not sudden catastrophe from above, but the slow, relentless brightening of the star itself. A gentle-seeming light that, over eons, turns deadly.
Now bring this back home. Our own sun is on the same path. Models suggest that in about 1 to 2 billion years, Earth will likely face similar pressures, shrinking oceans, thickening humidity, a climate system straining under extra solar energy. Optimistically speaking, we have time, but Kepler-452b may be living that future right now, under a star already about 10% more luminous than the sun. So let's begin to ask a sharper question. If Kepler-452 is our sun's older twin, is Kepler-452b a preview of Earth's destiny? And what would that actually feel like on the surface? Why an older sun can be bad news for oceans. If Kepler-452b really is Earth's future, we have to ask a brutal question. What happens to oceans when the sun's older twin keeps turning up the heat? Because as a star ages and brightens, the damage does not arrive all at once. It sneaks in through the atmosphere. First, more stellar energy means higher surface temperatures. That seems simple, but while a warm planet sounds pleasant, it starts a chain reaction. Hotter surfaces drive stronger evaporation from any oceans, lakes, and even soil. This means more water vapor rises into the air. And water vapor is not just a passive mist. It is one of the most powerful greenhouse gases we know. So the warmer the surface, the more water vapor in the atmosphere, and the more heat gets trapped. The system amplifies itself. On a world like Kepler-452b, receiving around 10% more energy than Earth, this feedback could be intense. In the hunt for alien life, we often celebrate liquid water, but here, water becomes the villain. As the lower atmosphere moistens, the upper atmosphere also starts to change. This is where the so-called moist greenhouse stage begins. In a moist greenhouse, more water vapor leaks into the upper layers of the atmosphere, high above the protective blanket where Earth keeps most of its water confined. There, ultraviolet light from the star can strike water molecules directly, splitting them into hydrogen and oxygen. Hydrogen, being extremely light, can escape the planet's gravity into space. Slowly, molecule by molecule, an ocean can be bled dry. It should be noted that this is not a dramatic tidal wave, but a quiet, relentless leak over hundreds of millions of years. Push the system a little harder and a tipping point appears. There is a limit to how much infrared heat a planet can radiate back into space. Once incoming energy from the star exceeds that limit, no extra surface heating can be balanced away. This means the climate slides into a runaway greenhouse. Temperatures skyrocket, clouds thicken, and any remaining surface water boils into a global steam envelope. Think Venus, but starting from something that once looked truly Earth-like. Now add Kepler-452b's size. With a radius about 1.6 times Earth's, its gravity could be nearly twice as strong. A massive planet can hold on to a thick atmosphere more easily. Depending on the mix of gases and clouds, that blanket might delay the moist greenhouse, reflecting extra light back to space. Or it could accelerate the disaster by trapping even more heat. So it's time to find out the truth. Given Kepler-452's advanced age and extra brightness, is Kepler-452b just entering this dangerous transition right now? Or has it already crossed the line into a permanently steam-shrouded world, its ancient oceans long since boiled away? Discovery story: how we found Earth's cousin. To answer that, we have to rewind the story. Before we can say what Kepler-452b might feel like, we need to understand how we even noticed this distant world in the first place. After all, how do you detect a planet you can't see around a star 1,400 light-years away? In the hunt for alien life, NASA's Kepler mission took a bold approach. Instead of hopping from star to star, Kepler stared at one single patch of sky for years. No dramatic slewing, no scenic tours of the Milky Way, just patient watching. The goal was statistical. Measure how common Earth-sized planets in the habitable Goldilocks zone really are. If even a tiny fraction of those distant stars dimmed in a regular pattern, it would mean planets were everywhere. This means Kepler was looking for shadows. When a planet crosses in front of its star, the star's light dips by a tiny amount. Repeat that dip on a regular schedule, and you have an orbit. For Kepler-452, those dips were subtle but persistent. Every 385 days or so, the star's brightness fell by less than 1 part in 10,000. It should be noted that this is like noticing a house light dim because a single moth flew across it. But buried in that data was a world. By carefully modeling the depth and duration of those transits, astronomers estimated a planet about 1.6 times Earth's radius crossing Kepler-452's face. A year just slightly longer than ours. An orbit right in the star's habitable zone. At first glance, it looked like an older, slightly scaled up Earth. No continents, no oceans in the data yet, just a repeating pattern in a light curve whispering, there is something there. So let's begin to sharpen that picture. The size of the planet depends on the size of the star, so teams around the world re-examined Kepler-452 itself. They took spectra, measured how the star's light is spread across colors, and used stellar evolution models to refine its temperature, radius, and age. As the star's properties came into focus, so did the planets. A bit more insulation than Earth, a super-Earth radius, an orbit that felt eerily familiar. That is why, in 2015, the announcement exploded across headlines. Here was one of the first reasonably Earth-sized planets in the habitable zone of a sun-like star. Earth's cousin, people called it. Optimistically speaking, it sounded like a world that could host oceans, clouds, perhaps even life. But while the excitement was real, the uncertainties were too. We still do not know its mass precisely. Its atmosphere is completely unmeasured. We cannot resolve its surface. We only see a pixel that blinks. Every climate model, every story we tell about Kepler-452b is balanced on those fragile numbers. So how far can we really push them before we drift from science into wishful thinking? That is where we go next. From headlines to hard questions, is it really habitable? So if all our stories rest on fragile numbers, why did Kepler-452b explode into the headlines as Earth 2.0 and Earth's older cousin? For a moment, it sounded like we had skipped straight to the end of the hunt for alien life. Sun-like star, Earth-like orbit, a planet just a bit bigger than ours. Case closed, right? But while that early media framing was irresistible, the scientific picture was always more cautious. Kepler-452b does sit in its star's Goldilocks zone, but very close to the inner edge, and around a star that is already 1.5 to 2 billion years older than the Sun. This means the star is about 10% more luminous, and the planet receives roughly 10% more energy than Earth does. For a world that may have been habitable for billions of years, that extra sunlight starts to look less like a bonus and more like a slow-burning problem. From that tension, two competing narratives emerged. In the optimistic version, Kepler-452b is a lush super-Earth, a rocky planet with deep global oceans, thick reflective clouds, and an atmosphere that skillfully balances incoming starlight and outgoing heat. Surface gravity, perhaps 1.5 to 2 times Earth's, could help it hold on to that atmosphere, keeping liquid water stable under a bright white-yellow sky. Optimistically speaking, it could be a world where life had a head start on us. In the darker version, the same ingredients drive it toward a Venus-like fate. More insolation, an aging, brightening star, and billions of years of slow heating might already be pushing its climate toward a runaway greenhouse. Oceans would evaporate, water vapor would trap even more heat, and the upper atmosphere would bleed hydrogen into space. Imagine a surface where seas are shrinking, clouds thicken into a suffocating blanket, and the last temperate regions creep toward the poles. Which of these stories is closer to reality? It should be noted that even that 10% extra starlight does not guarantee disaster. A slightly different atmospheric mix, stronger weathering of rocks, or brighter cloud decks could still hold temperatures in a moderate, habitable range. But the star's age and higher luminosity do tilt the odds gently toward warming, not cooling. Here's the pattern interrupt. We only know the planet's radius and its orbit. No measured mass, no spectrum of the atmosphere, no direct glimpse of oceans, continents, or clouds. So let's begin asking a harder question. With so little data, how far can we really go in describing what life would be like there without drifting into pure fantasy? So it's time to find out the truth about how disciplined we can be. In the next segments, we will treat Kepler-452b as a laboratory for thought. We will run best case and worst case scenarios, test them against basic physics, and see which possible versions of this world survive. How sure are we really? The limits of our cosmic guesswork. So let's begin by drawing a very clear line between what we know and what we only suspect. In the hunt for alien life, Kepler-452b looks, at first glance, like a prime candidate, a planet in a year-long orbit around a sun-like star, sitting in the Goldilocks zone. But while that sounds wonderfully Earth-like, the truth is that our hard data are surprisingly thin. First, mass. We do not yet have a direct mass measurement for Kepler-452b. Transit observations tell us its radius is about 1.6 times that of Earth, but that is only half the story. Without mass, we cannot calculate density, and without density, we cannot say with confidence whether this world is truly rocky, like Earth, or partly wrapped in a thick layer of lighter materials, more like a mini Neptune. This means any surface gravity we mention, any talk of mountains, oceans, or solid ground, rests on model-based estimates, not direct weighing. It should be noted that the atmosphere is even more mysterious. We have no spectra of Kepler-452b, no chemical fingerprints, no cloud maps, no confirmed greenhouse gas levels. All we can do is take the energy it receives from its star, combine that with climate models, and explore a range of plausible atmospheres: thin and dry, Earth-like with oceans, or thick and greenhouse-dominated, like Venus. Whenever we describe sky color, cloud decks, or what a sunset might look like, we are stepping from data into informed speculation. Even the star itself carries uncertainty. Kepler-452 is thought to be perhaps 1.5 to 2 billion years older than our Sun, and roughly 10% more luminous. But those values come with error bars. Shift the age or brightness slightly, and you change how long Kepler-452b has been in its current climate regime, and how far it may have progressed toward a runaway greenhouse. Optimistically speaking, it might still be comfortably habitable. Pessimistically, it could already be on the brink of becoming another Venus. So it's time to find out the truth about our approach. In the next parts of this journey, we will bracket reality instead of pretending to pin it down. We will use Earth as a template for moderate climates, Venus as a warning for overheated worlds, and established climate models to fill in the gaps. We will never claim to know the exact temperature of a Kepler-452b afternoon, or the precise shape of its continents. And whenever we move from measurement to imagination, we will say so explicitly, turning the unknowns into part of the story. Because the real question is not just what Kepler-452b is like today, but which of its possible faces the universe has actually chosen. Big picture verdict. How friendly is this system to life? So if the universe has given Kepler-452b several possible faces, which one is most likely? In the hunt for alien life, we need a big picture verdict before we worry about the color of the sunsets or the taste of the air. It should be noted that unlike TRAPPIST-1, with its compact family of 7 worlds, the Kepler-452 system currently has only one confirmed planet. We are not dealing with a bustling miniature solar system where different planets sample different parts of the Goldilocks zone. Instead, all of our attention falls on a single, potentially habitable world orbiting alone. That makes Kepler-452b less like a crowded apartment block of planets and more like one solitary house at just the right distance from its star. So let's begin with the orbit. Kepler-452b goes around its star in about 385 days, only a few weeks longer than an Earth year. In terms of raw stellar energy, it receives roughly 10% more than Earth does. On paper, that still looks comfortably within the habitable range. The twist is the star itself. Kepler-452 is a Sun-like G-type star, but older and about 10% brighter, which means the same orbital distance is subtly more dangerous for surface oceans. Optimistically speaking, this setup is almost exactly what we hope to find in the hunt for alien life. A stable, Sun-like star, a nearly Earth-like orbit, a planet about 60% larger than Earth, probably with enough gravity to hold a thick atmosphere and power geological activity for billions of years. This means long-term climate regulation is at least plausible through volcanoes, mountain building, and perhaps even plate tectonics, slowly cycling carbon between air, rock, and ocean. But while that sounds like a recipe for a lush blue world, there is a serious catch. Kepler-452b orbits near the inner edge of the habitable zone for a star that has already brightened over time. The system may be in a transitional phase, shifting from comfortably wet to increasingly hot and dry. Are its oceans still widespread, or are they retreating toward the poles? Has the atmosphere thickened with water vapor and carbon dioxide, nudging the planet toward a runaway greenhouse? Or has some stabilizing feedback kept it Earth-like for longer? So it's time to find out the truth at a finer scale. From here, we will zoom in from this system-level verdict to the local experience. Stronger surface gravity, a denser atmosphere, the fate of its water, the violence or calm of its weather, and finally, what it might feel like to live out a 385-day year under an aging, brightening star. Super-Earth physics, living under 1.5 to 2 times Earth's gravity. So if Kepler-452b really is Earth's older cousin, how different does life feel when every moment is lived under extra weight? From here on, gravity is the quiet dictator of almost everything. We know that when a planet grows, its mass does not increase in a simple one-to-one way with its radius. For rocky worlds, the relationship is steeper. A planet about 1.6 times Earth's radius, like Kepler-452b, is not just 60% bigger in size. Using standard mass-radius models, this means it could be 4 to 5 times Earth's mass, with surface gravity perhaps 1.5 to 2 times stronger than what we experience here. What does that actually feel like, step by step? Imagine standing up and your body quietly protesting. Your weight has doubled, but your muscles have not. Every step is heavier, as if you are carrying someone on your back. You can still walk, but running becomes a short, exhausting sprint. Jumps reach only half the height, and landings slam into your knees and spine. It should be noted that even your heart has to work harder, constantly pushing blood against that extra pull. Over generations, humans born there would adapt. Deeper chests, thicker bones, stockier limbs. But visitors from Earth would tire quickly, and long stays without preparation might be dangerous. In the hunt for alien life, this quiet pressure could shape entire species into compact, low-slung forms hugging the ground. Gravity also sculpts the planet itself. On Earth, mountains like Everest rise nearly 9 kilometers before rock begins to flow and collapse under its own weight. On a 1.5 to 2 gram world, tall peaks are harder to sustain. The landscape may be more rounded, with squat mountain ranges and deep, compressed valleys. Rivers would carve steeper, narrower channels, and landslides could be more frequent because everything has more weight pressing downhill. A stronger pull also keeps the atmosphere closer to the surface. Air piles up into a denser blanket, especially if Kepler-452b began with more volatiles. This means higher air pressure at sea level, thicker skies, and more efficient trapping of heat. Day and night temperature swings could be gentler, even as the aging star brightens. Optimistically speaking, that might help keep parts of the planet habitable for longer, delaying a runaway greenhouse in some regions. For engineers, though, gravity is a relentless tax. Buildings must resist more force, but dense air actually helps. It can support stronger winds and more lift from wings and airships. Skyscrapers could still rise, built from advanced materials, yet every beam and support would be overbuilt by Earth standards. Lifting cargo costs more energy. Launching spacecraft to orbit demands far larger rockets. Even climbing a staircase becomes a small engineering problem for the human body. So let's begin to imagine culture under such conditions. What kind of sports evolve when leaping high is almost impossible, but strength and balance matter far more? Do cities spread outward in layered terraces instead of reaching for the sky? And most of all, how would native life forms be built to endure this constant weight? Broad, armored, and close to the ground, or something stranger? Because if gravity shapes their bodies and buildings this much, what will it do to their oceans, their storms, and their climate as the star keeps turning up the heat? Breathing the air, atmosphere, sky color, and clouds. If gravity reshapes bodies and buildings, what does it do to the air itself? Because on Kepler-452b, the sky is not just a backdrop, it is a physical presence pressing down on you. A larger, older, rocky planet has had billions of extra years to build and hold on to an atmosphere. With roughly 1.5 times Earth's gravity, Kepler-452b is very good at hanging on to gas molecules that Earth would slowly leak away. This means it is likely wrapped in a substantial, possibly thicker atmosphere than ours, with higher surface pressure that you would feel in your chest from the moment you step outside. So let's begin with the simple act of breathing. Imagine drawing in a breath that feels denser, wetter, almost like standing in a warm rainforest after heavy rain. The oxygen level might be similar, but the total pressure could be 50, 80, even 100% higher than on Earth. Each inhale would carry more gas per lungful.
You would adapt, but at first, it might feel like breathing through a slightly resistant mask, the air heavy and humid. Now look up. Kepler-452 is a G2 star, a near twin to our Sun, so Rayleigh scattering would still favor blue wavelengths. The daytime sky is probably blue, not red or purple. But while Earth's sky is a bright, open azure, a thicker atmosphere, rich in water vapor, haze, and aerosols, could shift Kepler-452b's sky toward a deeper cobalt or a milkier, almost opalescent blue. It should be noted that if greenhouse gases, like CO2, have built up as the star brightened, that haze could be persistent, softening shadows and making the horizon look slightly washed out. Clouds would behave differently too. Higher gravity compresses the lower atmosphere, squeezing convection into a more compact vertical space. Thunderheads could still tower, but their vertical extent might be capped lower, forming dense, muscular columns rather than the sprawling anvils we see on Earth. Low-level cloud decks could be thick and layered, like stacked weather systems hugging the terrain.
Pattern interrupt. What if storms feel slower but hit harder? With more mass in every cubic meter of air, winds would carry enormous momentum. Storm structures might move more slowly across the landscape, yet their downpours and gust fronts could be brutally intense, shaping how any habitable cities are built. In the hunt for alien life, greenhouse gases are double-edged. They keep a planet warm enough for liquid water, but on Kepler-452b, elevated CO2 and water vapor under a brightening star could make the air feel warmer and almost oppressive. Haze would often blur the distance, and sunsets might be spectacular, deep oranges and blood-red bands as thick air scatters the last light. So it's time to find out the truth from a personal angle. Picture standing on a ridge. Above you, a slightly smaller, whiter sun than ours, perhaps more glaring at noon through a pale halo. Around you, slow-moving, massive cloud systems dominating the horizon. Would this world still feel comfortably Earth-like, or just a bit too close to the edge? Because next, we have to ask what that edge means for oceans, rainfall, and whether Kepler-452b is quietly slipping out of the Goldilocks zone altogether. Water worlds and dying seas, two ocean scenarios. So if Kepler-452b is hovering on the edge of comfort, what does that actually look like from sea level? In the hunt for alien life, oceans are often the real decision makers. They set the climate, feed the clouds, and decide whether a planet feels like home or like a warning. So let's begin with the optimistic version, a wet Kepler-452b. Imagine a world where deep global oceans wrap almost all the way around the globe, hundreds or even thousands of meters deep, with only scattered continents breaking the surface. The higher energy from its slightly brighter star drives a powerful water cycle, intense evaporation over warm seas, towering storm systems, and a thick, bright cloud deck that reflects a lot of that extra starlight back into space. This means the planet might stabilize itself, using those clouds as a kind of reflective shield. Under that shield, the oceans would feel different from Earth's. Surface gravity, perhaps 1.5 to 2 times higher, presses down on every wave. Swells do not leap as high, but each one carries far more force, slamming into rocky coasts like slow, heavy hammers. Currents become denser and more layered, with warm surface water sitting stubbornly on top of colder, saltier depths. It should be noted that such stratified oceans could trap heat near the surface, making the air above the water heavy, humid, and endlessly hazy. Walking along those shores, your lungs would work harder, not only against the strong gravity, but through a thick, moisture-laden atmosphere. Distant horizons blur behind slow-moving, massive cloud systems that rarely break. Is this still a comfortably habitable, Earth-like world, or something more alien, wearing a familiar mask? Now contrast that with the darker scenario, a drying Kepler-452b. Over billions of years, even modest water loss to space and to the deep interior chips away at the oceans. As the star brightens, equatorial seas boil off first, retreating toward the poles. What used to be blue belts become vast, sun-baked desert zones, where air rising from the scorched surface fuels rare but devastating storms that dump months of rain in a single day. With less open water, there is less evaporation. Fewer clouds form. More of the star's energy punches straight through the thinning shield to heat the ground. This means the feedback loop tightens. Hotter surface, drier air, shrinking seas, and a climate sliding step by step toward a runaway greenhouse phase. So it's time to find out the truth. If you lived there, would your civilization be clustered around shrinking polar coasts, watching the tide lines creep downward each century, or sailing vast, stormy seas beneath a bright, reflective cloud shield? Weather on a heavy world, storms, winds, and seasons. If the coasts are shrinking, what is the sky doing above them? On Kepler-452b, climate change would not just creep across maps, it would roar overhead. Because this planet orbits a sun-like star in roughly 385 days, its year would feel strangely familiar. Spring, summer, autumn, winter. They could all exist here, driven by the same basic physics that shapes Earth's seasons. If Kepler-452b has even a modest axial tilt, the extra 10% starlight means summers would be slightly more intense, winters slightly softer, and the contrast between them a little sharper than we experience at home. But while the calendar might look familiar, the weather would not. With 1.5 to 2 times Earth's gravity, the atmosphere is likely pulled into a denser, lower blanket. This means air near the surface could be thicker, heavier, and more tightly packed. Winds might not reach the screaming speeds of a thin, high-altitude jet stream, yet every gust would carry far more momentum. A breeze that looks like 30 kilometers per hour on paper could feel like walking through a moving wall. It should be noted that this denser air changes storms from the ground up. Updrafts struggle more against gravity, so clouds would be vertically compressed, but sprawling. Imagine storm systems that stretch across continents, their tops lower than Earth's towering anvil clouds, but their bases dark, layered, and unbroken from horizon to horizon. In the hunt for alien life, this kind of energetic, water-rich atmosphere is actually promising because it keeps temperatures more even, but it also makes the weather relentless. Over warm oceans, the extrastellar energy is fuel. Optimistically speaking, if Kepler-452b still holds vast seas, we might see megastorms, hurricanes broader than any on Earth, their eyes hundreds of kilometers wide, persisting not for days, but for weeks as they track slowly around the planet. The high gravity squeezes them downward, yet sideways they grow, wrapped in dense, spiraling rain bands that barely weaken when they hit land. Daily life under such a sky would be intense. Raindrops fall faster in higher gravity, hitting like tiny pebbles instead of gentle taps. Downpours would sound like continuous applause on rooftops, and walking outside in a heavy squall might feel like stepping into a pressure washer. Lightning would lace through thick, moisture-laden clouds, turning night into a flickering strobe. Between storms, the air could feel heavy and still, as if the entire atmosphere is holding its breath before the next outburst. So how would a civilization cope with this kind of planet-wide turbulence? This means architecture hugs the ground, low, aerodynamic buildings, domed roofs, and structures anchored deep into bedrock. Cities might be partially underground, or even embedded into coastal cliffs, using the planet itself as a windbreak. Weather forecasting would not be a casual convenience. It would be a life or death science, with orbital satellites tracking storm belts the way we track asteroid threats. So let's begin to ask a deeper question. Under skies like this, what kind of culture, technology, and psychology would evolve? And how close would they be to losing their world altogether? A day in the life, walking, working, and building in 2G. If you could step through a portal and stand on Kepler-452b right now, what would your body actually feel in that extra pull of gravity? Not the abstract number, about twice Earth's, But the moment your knees lock and your lungs protest. In the hunt for alien life, we often talk about orbits, atmospheres, and habitable zones. But life, if it exists here, would experience this planet one step at a time. For an unadapted human from Earth, that first step would be a shock. Your legs feel as if someone secretly strapped weights to your thighs. Walking becomes a sequence of short, careful steps, each one a small negotiation with the ground. After a single flight of stairs, your heart hammers, your breath comes fast, and there is a constant sense of weight pressing down through your spine and joints. Climbing a hill? That is no longer casual exercise. It is a deliberate expedition. You would lean forward more, plant your feet wider, and your muscles would burn in half the distance you expect. It should be noted that even standing still for long periods would be hard work for an Earth-normal body. Doctors here would talk about compression injuries the way we talk about back pain. But while visitors would struggle, long-adapted inhabitants of this world would be something else entirely. Over generations, natural selection and culture would sculpt people into shorter, stockier builds with thick bones, powerful hearts and lungs, and deep chest cavities to move dense air efficiently. Children would grow up in a society where every unnecessary movement has a cost. This means cultural norms might celebrate stillness, efficiency, and endurance rather than speed. A long-distance walker who can cross a plateau in 2G might be treated with the same awe we reserve for elite marathon runners. Now imagine the cities they build. High, needle-like skyscrapers are possible in our engineering fantasies, but here, architecture learns humility. Most buildings squat low and wide, with thick supports and broad foundations to spread the load. Multi-story structures exist, yet every extra floor demands stronger materials and more energy to move people and cargo vertically. Elevators draw serious power. Stairs are steeper, shorter, and broken into frequent landings, because each climb is an effort. Pattern interrupt. What about flying? On Earth, we take for granted that airplanes can lift us into the sky. On Kepler-452b, wings must work against a heavier pull, and very likely, a dense atmosphere. Aircraft use high-torque engines and reinforced frames. Every takeoff is expensive. So let's begin to see transport differently. Ground vehicles dominate daily life, rolling on strong suspensions and oversized brakes. Their motors tuned for torque rather than speed. Optimistically speaking, a person born here would seem astonishingly strong to us. A toolbox that feels punishingly heavy to an Earth visitor is just a standard work kit. Construction workers lift Earth-normal weights with what looks like casual ease, yet their tasks are slower, more methodical, because every mistake costs energy and strain. So it's time to find out the truth about this world society. In a place where the ground itself fights every motion, how does that shape power, inequality, and the technologies a civilization chooses to pursue next? If life evolved there, alien biology under a brightening sun. But what if the real power on Kepler-452b does not belong to machines or megacities at all? It belongs to the biology that managed to beat this heavy, slowly overheating world. So let's begin with the basic rules of that game. On a planet with perhaps nearly twice Earth's surface gravity, tall, spindly life is punished. High gravity favors compact, sturdy body plans, and a dense atmosphere with strong weather systems rewards anything that can keep a low profile and stay anchored when the winds roar. This means evolution is pushed toward shapes that waste nothing and hold tight. Picture the plant analogs first. Forests here would not look like our redwoods. They would be more like living fortresses. Low, interlocking canopies hugging the ground, with broad, overlapping leaves forming armored mats a few meters high at most. Flexible, but incredibly tough stems would bend under their own weight and under storm gusts without snapping, more like muscle than wood. It should be noted that to resist erosion and flooding on such a massive world, root systems might plunge tens of meters down, threading into fractures in the bedrock, turning whole hillsides into single, cooperative organisms. In the hunt for alien life, we often imagine graceful creatures leaping across alien planes. On Kepler-452b, leaping is expensive. Animal analogs would likely be squat and muscular, with wide, low centers of gravity. Many might have multiple limbs, not for speed, but for stability, like living walking frames pressed close to the ground. Powerful circulatory systems would be essential just to move blood and oxygen against the pole of the planet, with slow, rolling gaits optimized for energy efficiency rather than sprinting. Why rush when every vertical centimeter you lift your body costs so much? Now add the slow menace of a brightening star. Kepler-452 shines about 10% more intensely than our Sun and is older, meaning the long-term trend is upward. Life that endures here must plan, in a biological sense, for a future that is always warmer. Species creep poleward over millions of years, or retreat into deeper oceans where temperatures are buffered. Others evolve reflective surfaces, pale, mirror-like leaves, heat-dissipating frills, even shimmering skins that scatter excess light back into space. Some lineages might simply abandon the day. Nocturnal ecosystems could dominate the lowlands, with eyes tuned to starlight and bioluminescent signals replacing color. Burrowing and reef-building species would construct insulated refuges, turning the planet into a patchwork of microclimates. And if intelligence arose in the system, under that slow stellar countdown, how would it think? A civilization here would grow up with the knowledge that its Goldilocks zone is temporary. So it's time to find out the truth. Does every science, every religion, every political argument revolve around managing a world that is, by definition, on borrowed time? Civilization's on the clock, engineering a dying climate. If your entire civilization knows the clock is ticking, how do you build a future? On Kepler-452b, that question would not be poetic. It would be policy. Over hundreds of millions of years, its sun-like star brightens, turning a once comfortable Goldilocks zone into a slow-motion trap. This means that even tiny increases in stellar luminosity, just a few %, can push the climate past what oceans, rocks, and clouds can naturally buffer. So at some point, any technological species here faces a brutal choice: intervene in the planet itself or leave. In the hunt for alien life, we often ask whether a world is habitable. Here, the deeper question is whether it can be kept habitable. It should be noted that Kepler-452b already receives about 10% more energy than Earth from its star. Optimistically speaking, that might start as a pleasant, mild greenhouse. Over time, it becomes a creeping fever. So let's begin with planetary scale engineering. One response is to dim the sky. They could inject reflective aerosols high into the atmosphere, brightening the planet and bouncing starlight back into space. Imagine engineered volcanic winters, carefully tuned decade by decade. Or perhaps they construct vast orbital shades, thin, shimmering screens parked slightly sunward in orbit, trimming the star's glare by just enough to reset the thermostat. Engineered cloud systems could be another lever. By seeding specific regions of the atmosphere over oceans, they might thicken bright, low clouds, raising the overall albedo of the planet. But while these ideas sound elegant, they are also dangerous. A miscalculation in shade density or aerosol chemistry could tip Kepler-452b into global drought, or even trigger the very runaway greenhouse they are trying to avoid. Meanwhile, the surface infrastructure adapts. As low latitudes bake, cities migrate poleward or climb to higher elevations, chasing cooler air. Some populations retreat underground, where thick rock shields them from heat and radiation, building cavern megacities that echo with artificial daylight. Others might move underwater, using the oceans as a thermal blanket, surrounding themselves with cooled, filtered seawater, while the surface slowly scorches. Agriculture transforms as well. Traditional open-field farming gives way to closed, vertical habitats with tightly controlled climates designed to squeeze food from hotter, drier conditions. Entire valley systems may be roofed over, turning into sealed biospheres, each a carefully monitored experiment in survival. And culturally, this long emergency seeps into everything. Religions might preach stewardship of a fragile sky, elevating climate engineers to a priest-like status while fearing their mistakes. Philosophies debate whether it is moral to rewire a whole atmosphere for the benefit of one species. Political systems rise and fall over competing geoengineering plans, with factions arguing to shade more, to shade less, or to abandon the planet entirely. So it's time to find out the truth. If such a civilization exists, or once existed, on Kepler-452b, their entire history may be a story of racing their own star. The real mystery is whether their final choice was to master their world, to leave it, or to do something far more radical that we have not yet imagined. Could we live there? Human colonists on Kepler-452b. If their choice was radical, what would ours be? Because before we even ask how an alien civilization might adapt to Kepler-452b, we have to face a harder question. Could we ever live there ourselves? On paper, this planet looks temptingly Earth-like. In reality, it sits 1,400 light-years away. With our current rockets, that is not just a long trip, it is effectively unreachable. So it should be noted that when we talk about human colonists on Kepler-452b, we are stepping firmly into the far future, using this world as a thought experiment in how life adapts to a demanding environment.
And demanding is the right word. Kepler-452b is about 60% larger than Earth, which likely means surface gravity of 1.5 to maybe 2 times what we are used to. Imagine your body suddenly weighing twice as much. Your heart works harder, your joints complain, your balance feels subtly wrong every time you move. Now add a probably denser atmosphere, a warmer global climate, and potentially higher radiation if the planet's magnetosphere is weaker or shaped differently. Still sound like a second home? So let's begin with biology. In the hunt for alien life, we often talk about evolution, reshaping organisms over millions of years. Here, we would be turning that lens on ourselves. Long-term genetic modification could select for denser bones, more powerful hearts, and stronger connective tissue. Children developing entirely in high gravity might grow shorter, with barrel-like chests and thicker limbs, optimized for a heavier world. Medical technology would shadow them from birth, monitoring blood pressure, reinforcing weak vessels, perhaps even using implanted pumps to help the heart during exertion. But while biology can bend, it helps if technology does some of the heavy lifting. This means exoskeletons that quietly amplify every step, turning a crushing hike into a manageable walk. Pressurized habitats could tune the atmosphere for ideal oxygen levels and comfortable pressures, shielding colonists from any toxic gases or excess radiation outside. Cities might sprawl outward rather than upward, with low, wide structures, moving walkways, and transit systems designed so that very few people ever need to climb more than a single flight of stairs. Pattern interrupt. What if, instead of astronauts, we sent their great-great-grandchildren? Optimistically speaking, after just a few centuries, a population born and raised under Kepler-452b's sky might find our gravity light, our air thin, our sun strangely dim. Would they still think of themselves as human in the Earth sense? Or as something new, a branch of our species, shaped as much by this distant planet as by their ancestral home? So it's time to find out the truth by asking an even deeper question. What kind of culture and what kind of future could such a people build under a brightening star? Kepler-452b as Earth's mirror. Lessons from a hotter cousin. If Kepler-452b is home to such a culture, what exactly is their future telling us about ours? Because, in a very real sense, this world is not just an alien landscape. It is Earth's older reflection, a kind of time-lapse version of our own planet. already pushed further along the road we are destined to travel. Kepler-452b orbits a star so similar to the Sun that astronomers nicknamed it Earth's cousin. But while our Sun is middle-aged, Kepler-452 is likely 1.5 to 2 billion years older and about 10% brighter. This means the planet, in its Goldilocks zone, is being slow-cooked more intensely than Earth is today. What we see there, in principle, is a preview of how an Earth-like planet responds as its star quietly turns up the dial. It should be noted that the forces at work here are not mysterious. Human-driven climate change unfolds over decades to centuries as we rapidly add greenhouse gases and trap more heat. Stellar brightening unfolds over billions of years as nuclear reactions in a star's core gradually change its structure. But while the timescales are wildly different, the physics is strikingly similar. More incoming energy, more greenhouse warming, more stress on water and ice. On Kepler-452b, that extra 10% of starlight could nudge its atmosphere toward a moist greenhouse, where the upper air fills with water vapor that can be broken apart by ultraviolet light. Hydrogen escapes to space, oceans slowly shrink, and the surface dries. Optimistically speaking, this does not end habitability overnight. Instead, it carves out a long but finite window in which liquid water, complex chemistry, and perhaps technological life can flourish before the world tips toward a more Venus-like fate. In the hunt for alien life, that idea is both encouraging and sobering. Encouraging because it suggests that Earth-like planets may enjoy billions of years of relatively stable conditions, enough time for civilizations to arise, learn physics, build telescopes, and recognize what their star is doing. Sobering because if they ignore the trend, if they treat the slow warming as background noise rather than a signal, the window will still close, whether or not they burn fossil fuels.
So it's time to find out the truth about our own situation. Even if we magically erased every trace of human emissions tomorrow, Earth's habitability is not eternal. Stars age, planets evolve, continents shift, atmospheres leak, and biospheres either adapt to the new rules or fade into the geological record. Kepler-452b, hanging 1,400 light-years away, becomes less a curiosity and more a distant warning sign. It invites us to ask, will we treat slow, predictable planetary change as destiny, or as a challenge we are intelligent enough to anticipate and meet? And if other civilizations have already faced that question under their own brightening suns, what choices did they make? What we still don't know, and how we might find out. If Kepler-452b is a warning sign, what is it actually warning us about? Right now, the uncomfortable truth is that we do not really know. We have a silhouette of a planet, not a portrait. It should be noted that some of our biggest gaps are embarrassingly basic. We do not have a precise mass, which means we do not have a precise density. Is Kepler-452b a true rocky super-Earth? Or does it hide a thick envelope of lighter materials that makes it more mini-Neptune than Earth-like world? This means every detail about surface gravity, plate tectonics, and even whether you could stand on a solid surface is still up for debate. Then there is the atmosphere. We have no direct measurement of what, if anything, wraps this planet. Is it a clear, temperate mix like Earth's? A suffocating CO2 shroud like Venus? Or something far stranger, high hazes, deep clouds, or a steam-rich sky above a global ocean? In the hunt for alien life, that difference is everything. Without knowing the atmospheric composition, pressure, and cloud cover, we are largely guessing about temperature and habitability. We also do not know whether Kepler-452b has oceans at all, or active geology. Are there continents cycling carbon with the sky, volcanoes belching greenhouse gases, or a dead, locked crust, more like Mercury's. Any hints of biological activity, from subtle atmospheric imbalances to exotic pigments on the surface, are completely beyond our reach for now. Why are we so blind? Partly because Kepler-452b is far away, about 1,400 light-years from our solar system. Its star is relatively faint, and the planet is small. For transit spectroscopy, where we read starlight filtered through a planet's atmosphere, this is close to a worst-case scenario. Even powerful observatories like the James Webb Space Telescope struggle to pull out enough clean data from such a dim, tiny signal. So, let's begin to imagine what would change that. Future giant space telescopes, with mirrors 10 or even 15 meters across, could collect far more light from sun-like stars. Interferometers, linking multiple telescopes into one virtual mega-aperture, might resolve the light of an Earth-sized planet from the glare of its star. Add a precisely aligned star shade, and we could directly image a pale point like Kepler-452b, and spread its light into a spectrum, searching for oxygen, water vapor, or even industrial pollutants. Optimistically speaking, we do not have to wait for hardware alone. Better theoretical models of super-Earth interiors, of cloud feedbacks, and of exactly where the runaway greenhouse line falls for different atmospheres will narrow the range of plausible climates. Even without new photons, our predictions about this world can sharpen, so it's time to find out the truth. By the time we finally see a planet like Kepler-452b in detail, what will Earth look like? And will we recognize ourselves in that distant mirror, or see something far more unsettling? Reconstructing a world from shadows, how close did we get? So after all of that imagining, how solid is the world we just built? We should be honest with ourselves here, because in the hunt for alien life, wishful thinking can be just as dangerous as pessimism. Let's retrace the chain, step by step. We start with tiny dips in starlight as Kepler-452b crosses its star. From the depth and shape of those transits and the star's spectrum, we infer the planet's radius, its orbit, and the star's size, temperature, and age. This means we can estimate how much energy the planet receives, how long it has been bathed in that light, and where it sits relative to the Goldilocks zone. From there, we feed those numbers into climate models, different atmospheres, different ocean fractions, different cloud patterns. We ask whether a world 1.6 times Earth's radius, under a star perhaps 1.5 to 2 billion years older than the Sun, and about 10% brighter, tips toward temperate blue marble or slow-motion runaway greenhouse. Only then do we dare to layer on speculative biology and even civilizations watching their skies. But which parts of that stack are on bedrock, and which are on quicksand? The robust pieces are surprisingly clear. A larger radius almost certainly means higher surface gravity, perhaps 1.5 to 2 times Earth's. Near-Earth insolation, slightly higher than what we receive, is also well supported by the orbital period and stellar luminosity. And the star's age, older, more luminous, past its youthful volatility, anchors the idea that Kepler-452b has had a long, narrowing window of habitability. It should be noted that these three alone already shape any plausible scenario. High gravity favors a thick, long-lived atmosphere. An older, brightening star steadily pushes the climate toward the inner edge of the habitable zone. Optimistically speaking, that is exactly the kind of slow pressure that evolution can respond to. Everything above that, though, becomes mistier. Exact surface temperatures? Those depend on greenhouse gases we have not measured. Ocean coverage? We have no direct handle on whether it is a water-rich world or mostly land. Cloud decks that could reflect starlight or trap heat? Pure modeling. And of course, the existence, diversity, or absence of life, let alone civilizations, sits at the very top of that speculative pyramid. So why build the pyramid at all? Because stress testing these possibilities tells us where our physics is strong, where our climate intuition breaks, and how fragile the habitable label really is. So, let's begin to see Kepler-452b not just as a distant prize, but as a laboratory for our own theories.
Pattern interrupt. What if we are asking the wrong question entirely? If this is the best picture we can draw of an older Earth after years of data, what does that say about the thousands of other habitable zone planets we have barely glimpsed, and how careful we must be when we call any of them truly Earth-like? Imagining the sunset, a final walk across Kepler-452b. So if we are this uncertain from afar, what would it feel like to stop guessing and simply stand there on Kepler-452b and watch its day end? Imagine we walk together to the edge of a rocky coastline, or maybe a high basalt plateau that once sat above an ancient ocean. Every step is work. At roughly twice Earth's gravity, our boots press deep into the dust, and our knees complain with each slow rise. It should be noted that nothing here feels light. Our arms hang heavier, our heartbeat drums harder, and even turning our head reminds us we are visitors to a larger planet. We pause near the cliff. The sea below is dense, compressed by that same gravity, and the waves sound different. Not the familiar hiss of Earth's surf, but a deeper, continuous roar, as if the whole ocean is exhaling through clenched teeth. The air that carries that sound is warm and heavy, faintly humid, wrapping around us like a thick blanket. Above, the sky is a deep, saturated blue, darker than we are used to. The thick atmosphere scatters more light, and as the star sinks, that blue fades to a band of orange near the horizon. This means sunset here is not a sudden switch, but a long, drawn-out performance. Kepler-452, just a little brighter than our Sun and slightly older, seems reluctant to let go. Dense clouds hang low and compact, pressed down by gravity. Their upper edges catch the last light and glow gold, then crimson, then a deep blood red as the star dips behind them. In the hunt for alien life, we often talk about numbers and orbits, but here those abstract values are painted directly onto the sky. We feel the temperature easing, but not sharply. The thick air stores heat, softening the drop as evening comes. Far out over the darkening ocean, a low rumble rolls across the water. A storm cell is building, its anvil top sheared flat by high winds, lightning flickering behind the cloud like a slow, silent heartbeat. The star keeps sliding down, but just a bit more slowly than on Earth. On this 385-day world, the geometry of its orbit stretches the rhythm of sunrise and sunset. So let's begin to notice small differences. The length of the twilight, the way shadows cling to the rocks, the extra minute we get before true night. Optimistically speaking, a sky like this could have watched over forests, oceans, even civilizations adapting to the pull of 2 Gs. So it's time to find out the truth hiding inside this beauty. Because as we stand there, listening to the compressed surf and the first drops of rain, an unsettling thought lingers. This may be just one sunset in a very long decline. The star above us is slowly brightening, year after year, pushing this once Goldilocks world closer to the edge of a runaway greenhouse. And if Kepler-452b really is Earth's older cousin, then its fading evenings might also be a quiet preview of our own.
From an alien shore, back to Earth, what we learned. If this is a preview of our own sunset, what exactly did we just see? Stepping back from the shoreline of Kepler-452b, we can now sketch the planet as a whole. It should be noted that everything we have is filtered through sparse data and careful modeling, but a clear portrait emerges. This is most likely a super-Earth, about 60% larger than our own world, with gravity perhaps 1.5 to 2 times stronger. It orbits an older, brighter, sun-like star on a year only slightly longer than Earth's, and that star is slowly turning up the heat. This means Kepler-452b probably lives in a transitional climate state. It still sits in the habitable zone, but not the comfortable middle that Earth enjoys today. Instead, it occupies the warming inner edge, where small changes in starlight can tip oceans and atmospheres into very different futures. So it's time to find out the truth about those futures.
On one path, clouds and oceans fight back. A thick, water-rich atmosphere, bright reflective cloud decks, and strong circulation could keep the surface wet and temperate. Lakes might shrink toward higher latitudes, forests might hug the coasts, but liquid water would still flow. In the hunt for alien life, this is the optimistic scenario, a still habitable world adapting to a slowly brightening star. On the other path, the balance fails. As the star continues to brighten, evaporation feeds more water vapor into the air, strengthening the greenhouse effect. Clouds thin, oceans retreat, and the lower atmosphere fills with steam and CO2. The planet edges toward a Venus-like fate, not in a single catastrophe, but through a drawn-out fever that could last hundreds of millions of years. Which path did it take? We simply do not know. Yet even without that answer, we learned how such a world would feel. Heavier bodies under 1.5 to 2 grams gravity. Denser air that presses on your chest and carries sound a little too well. Landscapes that look strangely compact, with mountains that rise less, trees that grow lower, rivers that carve deeper, tighter valleys. Storms that are powerful but vertically compressed, unleashing their energy close to the ground. Any life here, whether simple microbes or complex ecosystems, would be built low, strong, and efficient, hugging the surface like a living armor.
And this is where Kepler-452b turns into a mirror. Its star is a near twin of our Sun, just 1.5 to 2 billion years older, reminding us that even the most stable-looking systems have finite habitable windows. Optimistically speaking, Earth still has a long future, but not an endless one. Our planet is not a static backdrop. It is a changing world, already on its own slow trajectory through stellar evolution. So let's begin to ask a harder question. If Kepler-452b really is our older cousin, what choices would a civilization there have faced as their sky brightened? And what does that imply for us? Your role in this story, curiosity, time, and our future. When you imagine Kepler-452b now, what do you feel? Is it comforting to think that Earth-like worlds can stay habitable for billions of years? Or unsettling to realize that even in the Goldilocks zone, the clock is always ticking? Both reactions are valid. In the hunt for alien life, Kepler-452b can look like a hopeful sign that planets such as ours endure. Its star has been shining for longer than the Sun. Its orbit is familiar. Its potential oceans and atmosphere feel almost home-like. But while that sounds reassuring, there is a quieter, sobering layer underneath. This world may already be slipping toward a runaway greenhouse, showing us that even the best cosmic real estate eventually changes beyond recognition. It should be noted that the timescales driving that transformation are immense. Kepler-452 brightens over hundreds of millions of years. Our Sun will do the same. Compared to that, a human lifetime is less than a blink. But our influence on Earth's climate does not operate on stellar timescales. It operates on centuries, decades, even years. This means that unlike the inhabitants of a distant, aging planet locked into its star's slow evolution, we still have real agency over what the next few hundred years on Earth look like. That contrast is easy to miss. We talk about Kepler-452b as if it were a distant story, safely removed from our daily lives. Pattern interrupt. It is not. The physics that might be pushing that planet toward a hotter future are the same physics we are testing right now with our own atmosphere, our own oceans, our own choices about energy and technology. So let's begin to see exoplanet science differently. It is not escapism, a way to daydream about running away from our problems to a fresh Earth 2.0. Studying a system like Kepler-452 sharpens our understanding of how fragile and rare a truly habitable window can be. When we model a super-Earth receiving 10% more starlight and watch its climate spiral, it makes the present-day stability of Earth feel more precious, not less. Carrying that long view changes how we think about environmental issues and innovation. Instead of asking only, what works for us right now, we can ask, what keeps our planet welcoming for minds that have not been born yet? Optimistically speaking, that perspective can guide everything from how we design cities to how we use space technology and telescopes. And if we stay curious, if we keep following the data from missions like Kepler, TESS, and the James Webb Space Telescope, we will be better prepared not just to interpret Kepler-452b, but to understand the many strange, beautiful worlds still waiting in the dark. So it's time to find out the truth about what those worlds can teach us next. Before you leave this world, subscribe to the next one. So where does that leave us, standing on this imaginary shoreline of Kepler-452b, watching an older sun burn a little too bright? In the hunt for alien life, we have just spent the last few minutes walking through an entire planet that we have never seen directly, built from a handful of photons and a lot of careful data and modeling. If that journey helped you feel what it might be like to live under that aging star, crushed by higher gravity, or listening to the last rain on a drying world, then this is only the beginning. We know that worlds like Kepler-452b are rare. It should be noted that this older Earth is 1,400 light-years away, and we may never send a probe, let alone a person. But while distance keeps our bodies at home, our curiosity can still orbit these distant systems. So, if you want to keep exploring planets like this, consider subscribing so you do not miss the next step. Did this video help you actually visualize Kepler-452b, from the color of its sky to the weight of its gravity? Then please take a moment to like the video. This means more people who care about big picture questions in the universe will actually see it. And tell us in the comments, which version of Kepler-452b do you find more compelling? The wet and thriving garden world, or the dry and dying planet slowly sliding into a runaway greenhouse? We are very curious to see which future you choose and why. Optimistically speaking, Kepler-452b is just one chapter in a much larger story about older Earths. So let's begin that story properly in the next episodes. We will look at other candidates that might show us different stages of Earth's long-term climate, and then contrast them with very different environments, tidally locked worlds with one permanent day and one endless night, and mini-Neptunes with deep, crushing atmospheres that challenge our idea of what a habitable planet can be. Future missions like Plato, Roman, and the next generation of ground-based telescopes will sharpen our view of these distant orbits. So it's time to find out the truth about how common Earth-like worlds really are, and how many of them sit in that delicate Goldilocks zone for only a brief moment. Because every time we tell the story of an exoplanet, we are also telling a story about us, about how fragile our own atmosphere is, about how temporary our comfortable window of habitability may be, about how easily a brightening star can turn a blue world into a warning. If you know someone who loves questions like that, share this video with them. We may never stand on Kepler-452b, but by staying curious together, we can explore thousands of worlds from right here, one deep dive at a time. And that journey can continue right now, with the next video waiting in your queue.